dive into the fascinating world of quantum mechanics, an area of physics that's not just academic, but also integral to our everyday lives. Quantum mechanics, a term that often evokes images of enigmatic equations and complex theories, is far more than an academic curiosity. It is the beating heart of modern technology. It's the invisible hand that powers our world in ways many of us may not even realize. Imagine a day without your smartphone, computer, or GPS. Tough, isn't it? Well, you have quantum mechanics to thank for all of them. The transistors in your devices, the heart of a modern computing, rely on quantum mechanics to function. These tiny switches, billions of which are embedded in your devices, use the principles of quantum mechanics to control the flow of electricity, storing and manipulating information. Then there's your GPS, a device that's become so integral to our lives. Did you know that it's quantum mechanics that makes it so accurate? Quantum mechanics helps correct for the effects of relativity, ensuring your GPS can pinpoint your location to within a few meters. And it's not just about gadgets. Quantum mechanics plays a crucial role in medical technology too. Magnetic resonance imaging, or MRI, a tool that has revolutionized the way we diagnose and understand human health, is a direct application of quantum mechanics. It uses the principles of quantum physics to create detailed images of the human body, aiding doctors in detecting and treating diseases. But the influence of quantum mechanics doesn't stop here. It's the key to understanding how atoms bond to form molecules, how stars shine, and even how the universe began. It's a fundamental part of the fabric of reality. So whether you're texting a friend, navigating through traffic, or getting a medical checkup, remember that quantum mechanics is silently at work, shaping our world in profound ways. So it's clear that quantum mechanics has a profound impact on our daily lives, even though we might not see it. Navigate through the realm of quantum physics, the study of the very small, where particles can exist in multiple places at once. This is a world that defies our everyday logic, a world where the impossible becomes possible. So what exactly is quantum mechanics? In a nutshell, it's a fundamental theory in physics that describes nature at the smallest scales of energy levels of atoms and subatomic particles. It's the science of the very, very small. The rules of quantum mechanics are radically different from the classical laws of physics we're used to. Let's dive a bit deeper. Quantum mechanics proposes that light and matter exhibit properties of both particles and waves, a concept known as wave-particle duality. This means that particles such as electrons and photons can behave like waves, and waves such as light can behave like particles. This is a significant departure from classical physics, where entities are either particles or waves, but never both. Then there's the concept of superposition. This is perhaps one of the most mind-bending principles of quantum mechanics. Superposition asserts that a quantum system, such as an electron in an atom, can exist in multiple states simultaneously. That is, until we measure it. Once we observe or measure the system, it chooses one state and all the other possibilities collapse. This is like saying a coin is both heads and tails until we look at it. Only then does it decide to be one or the other. But remember, these concepts are not just abstract ideas. They are grounded in experimental evidence and mathematical rigor. They have been put to the test and have withstood the scrutiny of countless experiments. Quantum mechanics, thus, presents a universe that is much different than what our senses perceive. It's a universe where the seemingly impossible becomes not just possible, but the norm. It's a universe that challenges our understanding and forces us to question the very nature of reality. Meet the quantum particles, the smallest building blocks of the universe. These particles are far from ordinary. They're not like the physical objects in our everyday life that we can see or touch. They're the pieces that make up everything around us, yet they behave in ways that challenge our understanding of reality. Take electrons, for instance. These tiny particles have a property called spin, but don't be fooled by the name. It's not like spinning a top. Instead, it's a quantum mechanical property that can only take certain values. In the world of quantum mechanics, something as simple as spinning becomes a complex dance of probabilities and uncertainties. Then we have photons, the particles of light. Unlike electrons, they have no mass and travel at the speed of light. They're responsible for letting us see the world around us and are central to the theories of quantum electrodynamics. Moving on, let's get acquainted with quarks. These are the constituents of protons and neutrons, the particles found in the nucleus of an atom. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. And here's a fun fact: you can never find a quark all by itself in nature. They're always found in combinations, a characteristic known as color confinement. Finally, let's not forget neutrinos. These elusive particles are so tiny and interact so weakly with matter that trillions of them pass through your body every second without you noticing. They're the ghosts of the quantum world, and their discovery has opened up new frontiers in understanding the universe. Each of these particles, with their unique properties and behaviors, plays a crucial role in the grand scheme of things. They interact, combine, and change in ways that give rise to the world as we know it. So, next time you look around, remember that at the heart of everything you see are these tiny, intriguing particles. These quirky quantum particles, with their unique behaviors, form the backbone of quantum mechanics. Explore Heisenberg's uncertainty principle, a cornerstone of quantum physics. At its core, Heisenberg's uncertainty principle is a simple concept, yet it has profound implications for our understanding of the universe. This principle tells us that we can't know both the position and momentum of a particle with absolute certainty. In simpler terms, the more precisely we know where a particle is, the less precisely we can know how fast it's moving, and vice versa. This isn't because of any flaw in our measurement tools, but is a fundamental aspect of nature itself. It's as if the universe has a built-in fuzziness that can't be cleared away, no matter how good our telescopes or microscopes get. Now, let's delve a bit deeper. The uncertainty principle doesn't say that we can't know both the position and momentum of a particle. Rather, it tells us that the product of the uncertainties in the position and momentum, that is, how off our measurements could be, must be at least as large as a tiny constant, known as Planck's constant. In other words, if we squeeze down the uncertainty in one measurement, the uncertainty in the other must balloon up to keep the product above this minimum value. The uncertainty principle has profound implications for the nature of reality. It tells us that the universe at its most fundamental level is a game of chance, not certainty. Particles don't have well-defined positions and speeds. Instead, they exist in a cloud of probabilities, popping in and out of existence in different places and with different speeds. This principle also underpins many other aspects of quantum physics, such as quantum tunneling, which allows particles to pass through barriers that, according to classical physics, they shouldn't be able to. The uncertainty principle thus introduces a fundamental fuzziness in the nature of the quantum world. Venture into the realm of quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. Quantum entanglement is a surreal concept that defies the norms of classical physics. It's like a cosmic connection that binds two particles together no matter how far apart they are. When two particles become entangled, they form a pair. What's fascinating is that the state of one particle is immediately linked to the state of its partner, irrespective of the distance between them. Imagine having two dice. In the classical world, if you roll the dice, the outcome of one die doesn't affect the other. But in the quantum world, if the dice were entangled, rolling one die would instantly determine the outcome of the other, no matter how far apart they are. It's like they're communicating faster than the speed of light, which is, according to Einstein's theory of relativity, impossible. This is why Einstein called it spooky action at a distance. Now, let's discuss the implications of this phenomenon. Quantum entanglement is the heart of quantum computing and cryptography. Quantum computers, unlike classical ones, can process vast amounts of data simultaneously. This is possible because of the entangled state of quantum bits or qubits, which allows them to hold more information than classical bits. Furthermore, quantum entanglement has significant implications for secure communications. In quantum cryptography, if two parties share an entangled pair of particles, they can communicate securely. Any attempt to intercept the communication would alter the state of the particles, revealing the eavesdropper. However, as mind-bending as quantum entanglement is, it's not without its limitations and challenges. The entanglement is fragile, and maintaining it over long distances is a significant hurdle. But scientists are continually working to overcome these challenges, pushing the boundaries of what's possible. Quantum entanglement, hence, opens up new dimensions in communication and computing. Scientists are just beginning to scratch the surface of this enigmatic phenomenon. As we delve deeper into the quantum world, who knows what incredible discoveries await us? Decipher the puzzling concept of quantum superposition with the help of Schrödinger's cat. Quantum superposition, a cornerstone of quantum mechanics, is the mind-bending idea that a quantum system can exist in multiple states all at once. But what does this really mean? To understand this, let's delve into the world of Schrödinger's cat, a thought experiment proposed by Austrian physicist Erwin Schrödinger. Imagine a cat inside a box out of your sight, along with a tiny amount of radioactive substance, a Geiger counter, and a vial of poison. The radioactive substance has a 50-50 chance of decaying within an hour. If it decays, the Geiger counter triggers and breaks the vial, releasing the poison and leading to the cat's demise. If it doesn't decay, the cat lives. So is the cat dead or alive? In our everyday world, we'd say the cat must be either dead or alive. But in the quantum world, things aren't that simple. According to quantum mechanics, until we open the box and observe, the cat is both dead and alive. It's in a superposition of states. Now you might be wondering, how can something be both dead and alive? Well, it's this paradox that Schrödinger wanted to highlight. Quantum superposition doesn't align with our common sense. But remember, quantum mechanics doesn't play by the rules of our everyday world. The moment we open the box and observe, the superposition collapses and the cat is found to be either dead or alive, not both. This is known as wave function collapse. The act of observation forces the cat out of superposition and into one definite state. This brings us to another fundamental aspect of quantum mechanics, its inherent probabilistic nature. Until observed, things don't have definite properties. Instead, they exist in a haze of probabilities. Superposition, thus, defies our everyday logic and introduces us to the probabilistic nature of the quantum world. Discover how quantum mechanics fuels modern technology. It's truly an intricate dance between the abstract theories of quantum mechanics and the tangible applications we see in our everyday technology. Let's start with semiconductors, the heartbeat of almost all electronic devices. These tiny components rely on the principles of quantum mechanics. You see, semiconductors are made from materials that, at their core, have properties determined by quantum states. These properties allow them to control electric current, a fundamental aspect in the functioning of devices like smartphones, computers, and even your digital wristwatch. Next, let's shine a light on lasers. The operation of lasers is a direct application of quantum mechanics. The trick lies in the principle of stimulated emission, a quantum mechanical process where a photon interacts with an excited electron, causing it to drop to a lower energy state and emit a photon of precisely the same energy. This process, repeated millions of times, gives us the intense, focused beam of light we know as a laser. But quantum mechanics doesn't just stop at your electronics and cool light beams. It's also at play in medical technology, particularly in magnetic resonance imaging or MRI. An MRI machine probes the spins of atomic nuclei, a property that is inherently quantum mechanical. By aligning these spins in a strong magnetic field, then disturbing them with a radio wave pulse, the MRI can form an image of the inside of your body, helping doctors diagnose and treat a myriad of conditions. From the microchips in your phone to the lasers in your DVD player and the MRI machine at your local hospital, quantum mechanics is deeply intertwined with the technology we use every day. It's the unsung hero, the silent partner, the invisible hand guiding modern technology. With quantum mechanics, we're able to push the boundaries of technology and achieve the impossible. So next time you're marveling at a piece of technology, remember the quantum world that's silently powering it. Get a glimpse of the future with quantum computing. Imagine a world where problems that take years to solve could potentially be solved in seconds. That's the kind of world quantum computing could bring us. Let's start by understanding what quantum computing is. In contrast to classical computing, which uses bits as the smallest unit of data, quantum computing uses quantum bits, or qubits. While a classical bit can be either a 0 or a 1, a qubit can be both 0 and 1 at the same time, thanks to a quantum phenomenon known as superposition. This ability to exist in multiple states simultaneously allows quantum computers to process a vast number of possibilities all at once, making them exponentially faster and more powerful than classical computers. Another key feature of quantum computing is entanglement, another strange quantum phenomenon. When qubits become entangled, the state of one qubit is directly related to the state of another, no matter how far apart they are. This allows quantum computers to perform complex calculations at a speed that is currently unimaginable with classical computing. But what does this mean for us and our future? The potential applications of quantum computing are staggering, from revolutionizing drug discovery by simulating complex molecular structures, to optimizing logistical problems, improving artificial intelligence, and even cracking most encryption algorithms used today. The possibilities are nearly endless. However, it's worth noting that quantum computing is still in its infancy. There are significant challenges to overcome, particularly in maintaining the stability of qubits. But scientists and researchers around the world are tirelessly working on it, inching us closer to this exciting future. Quantum computing, hence, holds the promise of revolutionizing our technological future. Just as classical computing transformed the world in the 20th century, quantum computing has the potential to define the 21st. It's a thrilling time to be alive, and we can't wait to see where this quantum leap in computing takes us. Ponder over the mysteries that quantum mechanics still holds and the road ahead. We've come a long way since the dawn of quantum mechanics in the early 20th century. However, the journey is far from over. Quantum mechanics continues to be a vibrant and intriguing field of research, continually challenging our understanding of the universe and pushing the boundaries of our technological capabilities. The road ahead is paved with exciting possibilities. Quantum mechanics offers us a chance to peer into the very heart of matter and energy. At the forefront of this research is the quantum gravity puzzle. Scientists are striving to unify quantum mechanics with Einstein's theory of general relativity, a puzzle that has eluded us for over a century. The solution could potentially revolutionize our understanding of the universe, from the tiniest particles to the vast expanses of the cosmos. Beyond the realm of pure science, the practical applications of quantum mechanics are also expanding. Quantum computing, as we discussed earlier, promises to revolutionize data processing and encryption. But that's just the tip of the quantum iceberg. Quantum sensors could significantly enhance our measurement capabilities with potential applications in navigation, climate science, and medical imaging. Then there's the tantalizing field of quantum teleportation. While it may sound like science fiction, researchers have already managed to teleport information between particles over considerable distances. This could pave the way for ultra-secure quantum communication networks. Quantum materials, another exciting area of research, could lead to the development of superconductors that work at room temperature, transforming energy generation and transmission. Finally, let's not forget about quantum biology. Yes, you heard that right. There's growing evidence that quantum effects play a role in biological processes from photosynthesis to bird navigation. Unraveling these mysteries could lead to fascinating insights into the nature of life itself. Quantum mechanics, therefore, remains a vibrant field of research with potential to transform our understanding of the universe. Recap the fascinating journey into the quantum world. In the past hour, we've delved deep into the heart of the universe, where the laws of classical physics take a back seat to the strange and wonderful world of quantum mechanics. We've seen how this field of study, once considered the domain of theoretical physicists, plays a pivotal role in our everyday lives. Our journey began with the recognition of the relevance of quantum mechanics. It's not just a theoretical playground. It's the key to understanding the fundamental nature of reality, from the tiniest particles to the largest celestial bodies. We then explored the building blocks of the universe, quantum particles. These particles behave in ways that can seem counterintuitive, even bizarre, to our macroscopic minds. But it's their unique properties that make the quantum world so fascinating and rich with potential. Next, we grappled with Heisenberg's uncertainty principle, which suggests that we can't know both the position and velocity of a particle with absolute certainty. This principle is at the heart of quantum mechanics, highlighting the inherent unpredictability of the quantum realm. We then delved into the phenomenon of quantum entanglement, often described as spooky action at a distance. This mind-bending concept shows us that particles can become entwined in such a way that the state of one can instantly affect the state of the other, no matter the distance between them. We also discussed the concept of quantum superposition, illustrated by the famous thought experiment of Schrödinger's cat. It's the idea that a quantum particle can exist in multiple states at once until it's observed. Finally, we looked at the future, exploring the revolutionary potential of quantum computing. This technology promises to solve complex problems far beyond the capabilities of classical computers, harnessing the power of quantum mechanics to transform our world. Thus, quantum mechanics, with all its quirks and mysteries, continues to shape our world and the way we understand the universe.